Hello to those of you who have joined us. We're just waiting for the time to come up and for a few more attendees to join, so we'll start shortly. Hello to those who have joined us. We shall soon start. I think a few more attendees will sign up, so we just wait another couple of minutes, a minute or two. We are almost ready to start. Maybe in South Africa, our time clock is 1 minute ahead of the rest of the world, so we'll just wait another minute. All right, almost there. We'll give another minute and then we'll give it a go. All right, I think we're going to start. At least we announced the time to start at this time, so I think we're going to kick off. Good day to those of you who joined from anywhere in the world. This is an open webinar. We're talking from South Africa, where it is 2 o'clock in the afternoon, just beyond 2 o'clock. My name is Jan Wiem. You will see on the left-hand side on the slide, it says the moderator is Pierre van der Spy. Pierre, unfortunately, is caught up in some urgent business, and he's on a plane somewhere in the world, so I'm standing in for him. So just before we start, we're going to host this about Ashton Arch Bridge. We'll have a presentation, and then there will be opportunity for questions and comments afterwards. But just before we do that, I want to share with you just an overview of the IABSE organization. There may be attendees who are not familiar with IABSE, so it will take a very short moment just to give an overview of the organization. So I'm going to share my screen. So if you bear with me for one moment, I'll do that right now. And then I must get my presentation going. Heinrich, can you see my presentation in presentation mode?
Yes, everything good.
All right. All right,
yes.
Thank you. So for those who have just joined, I'm giving a quick overview of the IABSE organization, which is the International Association for Bridge and Structural Engineering. The mission of IABSE is to exchange knowledge and to advance the practice of structural engineering worldwide. Often people think that IABSE is mainly for bridge engineering, which is not the case. It covers all aspects of structural engineering, from all types of structures to all types of materials, including the construction side of things. So as you can see, there's quite a large number of members in over 100 countries around the world. One of the real benefits from membership at IABSE is access to the journal, which is our flagship publication, the Structural Engineering International. And those of you who are familiar with the journal will know that it publishes interesting research, but also documentation about projects around the world. So one of the few journals in the world that have both academic research and project information of case studies and real engineering taking place. There are other publications such as the bulletins and the case studies, and all of those actually capture information that is of benefit for structural engineers. IABSE is mainly organized by the national groups, which form the backbone of the organization. So in the national groups, people meet one another and they have access to the international membership. The national groups actually are responsible for organizing events such as this one, but also for international events where people from all around the world can meet and mingle together. And I must say, one of the real benefits for me as an IABSE member is the good friendships and connections that I've made at these conferences. It takes a little bit of time, so in your first attendance at an international conference, you may feel a little bit out of place. But if you attend 1 or 2, 3, soon you start seeing the same people and really start building friendships and connections with like-minded people. And that is one of the real benefits of meeting others who are in the same frame of mind. A new contribution to the IABSE membership is actually the access to task groups. Now, the IABSE has technical commissions, 6 of those who manage the task groups. A task group is basically, can be anything from 2 to many people that decide on some other deliverable. It can be that they want to publish a code, a design code, or a specification, or a case study, or they want to publish good guidelines for anything. They approach the technical commissions and then they create a task group to work around that. The real aim is to have working groups or working members that deliver something. So task groups are normally restricted to 2 or 4 years in which they need to deliver something, and then they disband again. So anybody can form a task group. Any member can even get non-members to participate in task groups. As I said, one of the real benefits of IABSE is the annual events. Now, there are normally two large events, one in April, May, and another one in September, early September or late September. This year, the Congress in Nanjing is coming up soon. Those of you who have not registered can still do so, and really would like to encourage you to participate in that event. There's always activities for young engineers at IABSE with several benefits, as you can see on the screen. I'm not going to elaborate on that. And then this webinar, as well as other webinars and other relevant information, is captured on the IABSE learning page, e-learning page. So members have access to these, and these actually grow as the time goes by. The next webinar that will be organized by our group, the South African group, will cover the Omaruru River Bridge in Namibia. Our group is relatively small. We've got about 20 members scattered around quite a large country. We seldom get together as a real group, but these webinars are beginning to grow the group and to expand our membership locally. With that, then, I'm going to hand back to come back to the webinar that we want to present. And we've got our two participants, two presenters here with us, Abe Newmark and Heinrich van Wijk, who will both address us in presenting the new arch bridge in Ashton. Abe graduated many years ago as a civil engineer from the University of Pretoria. He spent his career as a bridge specialist on a major highway and other bridge projects in South Africa, the rest of Africa, and also in the Middle East. And with us is also Heinrich van Wijk, who is involved with structural analysis and design, and also looking at cable optimization and erection monitoring as a specialization side. Heinrich is also the immediate past president of the Concrete Society of Southern Africa, and I will leave it to them. They're going to share the presentation, and I would like to welcome them and say thank you for making themselves available for this opportunity.
Thank you, Prof. Could we just have confirmation that you can see our screen that we're sharing now?
Yes, we can see that, and your sound is clear, so go ahead.
Good, thank you.
Okay, thank you very much for those kind words, and also for the great privilege to be able to present on this forum. We're really grateful for that, and we trust that you will find our presentation worthwhile the time you're investing in it. Heinrich and I are going to share the slides. I'll start off with certain aspects, and Heinrich's going to focus more on the erection engineering and the design side, and then I'll close off with the launch, transverse launch operations, and then we will share questions and answers. As mentioned, the project is located in South Africa, at the southern tip of Africa, for those who might not be aware exactly where we are. This route is one of our strategic local and national routes, also a very important tourist route, and has been a historic link for the past 300 years in South Africa. The project entailed quite a large upgrading of an existing pass, and also links to two towns, and our bridge is located in the town of Ashton, which is at the start of the project. In this town, Ashton, there was a river crossing, the Kochmans River crossing, and This bridge was originally constructed in the 30s as a single lane structure and then widened in the 50s, basically by building a new bridge straddling the existing structure. On the pictures, you can actually see the soffit of the original arch and then the side arch beams and cantilevers that formed the wider structure. But as things go, the new route upgrading required a wider structure, and combined with that was the hydraulic inefficiency of this bridge. It wasn't aligned to the river channel direction properly. There was ongoing damage to the structure. Debris buildup was a common problem. The view you're looking at now and the subsequent pictures over the years shows the problems that happened at this crossing. You can actually see this is where the bridge is being overtopped during a large flooding of adjacent properties, and so forth. With the upgrading of this structure, a lot of options were evaluated. We looked at a voided slab deck with a temporary bypass through the river, voided slab deck constructed in half widths, the single span tied arch launched transversely, and also the usual precast beam bridge options, either with a temporary bypass or half widths. Eventually, without going into too much detail, we have published some papers on this regard already for further reading. We found that the transversely tied arched launched transversely provided the optimum solution. If we look at the construction costs, obviously with the longer span, there was a premium to be paid for capital costs, but we also evaluated the indirect costs for this crossing, and with traffic delays on this major route and so forth, our eventual conclusion was that the arch was the optimum solution. So, because the key points that achieved was that the route can remain open during construction. It will provide a much better hydraulic crossing, and with the transverse launching planned to happen over a weekend, minimal impact on traffic and so forth will occur. The image you're looking at now was actually original Revit image developed during the design process, and it just shows one. If you look at the pictures later on, one can show how true to life these images can actually be these days. Just a very quick, in the presentation, we're going to refer to a few components, just to make sure we're all on the same aspect of the structure. The vertical hangers, the tie beam, which provides or resists the thrust of the arch rib. All the forces join at the two spring points, and the rise of the arch, obviously the total height. Just a few brief statistics as well, or details of the arch. We've got 4 traffic lanes, 2.4 meter sidewalks on both sides. The overall height is 22 meters. We've got 15.5 meter wishbones that the longitudinal tie beam are post-tensioned, and then we've got a coffered deck with longitudinal and transverse post-tensioned beams, keeping in mind that the deck spans between the two tie beams. We've got 48 hangers or stake cables. Hanger is probably the best word for that, and these are connected to the arch tie beam and arch rib with anchor plates or anchor brackets. Then I'll just touch on a few design and construction considerations, more on from the conceptual perspective. Obviously, with a major crossing like this, the bridge aesthetics and structural form plays an integral role, and we also feel that the new arch does, in a way, pay attention to the existing arch form of the original bridge. As mentioned, the ability of this structure to span over the entire river made a significant improvement to the hydraulic efficiency. Because of the suspended roadway with reduced vertical clearance of deck depth, we could achieve tie-ins with the approaches and also provide improved hydraulic clearance. A V-hanger configuration was adopted in preference to vertical to also assist with the aesthetic appearance. And we believe the visually appealing light deck, especially viewed from the side, does express itself nicely, but it also focuses on the force configuration of the structure. There's a actual picture of the arch, very close to the view that we saw earlier, and you can actually pick up the skew river crossing and the arch managing or effectively spanning the whole river. That's a different view from a drone picture, and I think this also illustrates what was tried to achieve with this structure. In South Africa, we generally prefer concrete bridges from a historic perspective, and in this instance, we also focused or decided to use concrete as the primary construction material. Our contractors are familiar with the use of concrete, and everybody's comfortable with all the durability and design requirements. Obviously, a steel arch would also have been an option. As mentioned already, the spring points required special attention with the steel volumes that were cast or contained in them, and combined with the concrete volumes and the thermal behavior of the concrete. Our concrete specialist, Philip Renee, had extensive experience in this regard, and with Heinrich and the contractor, we provided a large degree of input on making sure that the end result in these critical parts and also the rest of the arch was satisfactory. That's just a few images showing how we basically had mini tremies where we poured the concrete from the bottom up, and we had inclined shutters that were incrementally closed as we cast that part of the arch. Then we can just go through a few other parts of the temporary works. In a sense, the temporary works were very extensive. We initially foresaw that the contractor would use steel heavy-duty columns, but they felt that concrete demolished afterwards was more efficient. So that's part of the temporary works being constructed. They used temporary caissoons in the river to construct the support structure. We had shoring around the abutment locations, because we had to go down quite deep, as you can see there, with using the laborers as a scale factor, and that had to be extended when we went across to the new foundations. This is the false work shortly after completion, heavy-duty girders. Although it seems quite an extensive, or it is quite an extensive construction, the contractor arranged a buyback scheme for the specially manufactured girders, so they're still in use today on other projects of this nature. These girders were supported on sand jacks to allow removal after completion of the main structure. Soffit formwork and the arch spring point. You can see the coffer system that was provided to construct and cast the deck in stages. And just the last view of the arch rib as it was constructed in segments over a period of time on false work. Okay, then I will briefly touch on one special aspect of interest, and this is where our South African steel manufacturing skills were really pushed to the limit. The hanger anchors are very important components, and the failure of those would obviously be a critical failure element of the whole structure. Although we've designed for hanger out, single hanger out scenarios, and we found that both the design of the item itself and also the connection into the arch required a lot of design and construction input, and we work closely with our UK team who have extensive experience in this regard, and eventually, after some experimentation and so forth, we concluded that compound welded plate anchors were the most suited for our conditions and availability of materials, and it also gave us, with the various plates and welds, we achieved a significant amount of redundancy in the component. This is just some views with class EXC4, exclusion class 4 quality control, which basically meant that every weld was tested and recorded, and the quality records are linked to actual positions for the life of the structure, so that can all be evaluated. This is a few photos from the machining of those components, and you can also see some of the quality control procedures that were implemented, and the size of those units. They were in the order of 1.6 tons each. Corrosion protection, thermal zinc spray was also selected after some tests on galvanized coatings, and these units were just too massive in terms of thickness to make that effective. And then we followed that with intermediate and epoxy and polyurethane coats. Installation was done by a specially developed rig, where we brought it in with tower cranes, and then the units were alignment of very closely, because as you may realize that the alignment between top and bottom units and had to comply with hanger cable fleet angle constraints to make sure that there's no secondary forces introduced into the cables. So this was quite a exercise to manage to do that. Combined with that, when the tolerances on the plates and the jacking jacking washer plates had to be further enhanced by machining of the washer plates because of allowable tolerances on your very short divvy duct bars, keeping in mind that with these plates being manufactured and heat treated and so on, there was always a degree of curvature that couldn't be avoided because of the thickness of the steel plates and the multiple welds. So we solved that by assessing the maximum deviation, and we measured each plate in situ, and then categorized washer plates into different angles, which to ensure that those surfaces were compatible and within tolerances. This is just some pictures of the data that we assembled and the washer plates having been machined, and then these units were then tensioned and with divvy duct jacks, bearing in mind that it was very short anchors and or bars which had to be tensioned very carefully due to the extensive losses due to seating and so forth as a percentage of the force. And we physically did extensive lift-off tests to confirm that the forces were induced into the plates. Thanks. That's enough for me for the moment. Heinrich is going to take over at this point.
Okay. Thanks, Abe. I'm going to carry on discussing the post-tensioning activities of the main deck. And as Abe mentioned, the bridge is it's maybe not that conventional for a tied arch bridge, because the deck, which is a tension element, is made up of concrete. So for the deck to be able to take all of that tension induced by the arch, you have to post-tension or pre-stress the deck, so that this concrete element is always under compression and with the pre-stressing. So just put on the, see if I can get the laser pen. So the two tie beams that connect to the arch had 6 tendons each, and these were all concentric straight cables with 31 strands each. And those straight cables were there basically to keep the tie beam in compression all the time. In between the outer tie beams, you had more conventional rectangular beams with also with fairly straight cables to keep the deck in compression. Transversely, the deck spans between the tie beams, and those beams were also tensioned, but those were draped cables transversely just to carry the self weight of the deck. So during tensioning of especially the primary beams, you would expect that straight cables has quite straightforward tendon elongation calculations, where you calculate your friction and your wobble factor to determine your extensions. But what we found with these cables is that the extensions were less than anticipated. So just as an illustration, we show the graph of what we calculated. We were expecting about 500 plus millimeters of elongation. And when we measured it on site, the elongation was still linear, but significantly less than what we had in our design. And we had to brainstorm the reason and figure out the reason for these under extensions. And we did test tensioning on all of the strands without locking off the cables, just to get an idea and a scatter of a wobble factor that can account for this excessive or additional friction. So we calibrated our wobble factor in this way, and we updated our FEM models to also reflect this behavior. But we also looked at other reasons for what could possibly be the reason for the under extensions, and we looked at our installation method. We know that for conventional smaller span bridges, the pushing method is your preferred method of installing strands, and that's what the contractor did. But just to ensure that any entanglement is not the reason for these under extensions, we reinstalled the cables with the pulling method. So as you can see in the bottom left picture, the strands were bundled together and pulled through with a winch. And I think the nice aspect of using the pulling method is that you're able to guarantee a good lay of cables in your ducts, and you reduce the possibility of any entanglement. So after we reinstalled the cables and calibrated our wobble factors, we were able to correctly predict the extensions. Okay, I'm going to talk on some topics regarding the structural modeling. The primary model was done with Bentley's RM bridge quite a while back now, and the full design was done with this model. The RM bridge was a grillage model, and several years later, actually just prior to construction, we had our UK colleagues do a peer review on the model, and they used Sophistic. And the Sophistic model was a bit different in that it uses quadrilateral shell elements for the deck slab and the springing points. And also because it was closer to construction time, we knew what the contractor's plans were for the temporary staging, and this could be modeled accurately. So we had these two models and we calibrated them, and we got the same behavior from the two models, which gave us confidence for doing the erection engineering. I'll just play a quick clip of the 3D rendering of the sophistic model going through the construction stages. So all of there were quite a few construction stages with the sophistic model. Oops, I'm just going to go through that again. Just bear with me. Okay, I'll let it play. So with the construction stages, prior to post-tensioning the longitudinal beams, we casted alternating slabs, as you'll see in the next construction stage. That was done so that the post-tensioning would flow into the beams as opposed to being diverted into the slab. And then we tensioned the end beams for bursting, and then the transverse beams. You can see and then the internal beams, cantilever beams, and then the arch ribs. And then the tensioning of the stay cable, the first stage of stay cables or hanger cables. And we actually broke up the tensioning of the hangers into two stages, where the first stage is essentially to pick up most of the dead load of the structure. And then you could say that the second stage was to almost optimize the stress distribution in the structure. Okay, I thought on the structural monitoring topic, it's the determination of the stay cables it's quite an interesting topic, or I found it quite interesting. And so in determining the stay cable forces, we had to choose a target, and we decided, I'm just going to use the deck here as an example, but we chose installation cable forces so that we could aim for a specific deck profile. In this instance, you could look at the bottom left, we've got a parabolic shape for the 110-meter deck span. And we wanted to determine the cable forces that would give us a good deck profile. And in this instance, a good deck profile gives us a good bending moments or good stress distribution. So the way we determined this input cable forces is with the so-called unit load method. And I'm going to attempt to explain this in 5 minutes. So what we did here was this unit load method entails applying an arbitrary unit load to a set of cables. And you could, I think we used 1000 kilonewtons, which is, I'm trying to illustrate with the blue bar here. And we analyzed the structure, single linear run. And we looked at the resulting forces on the adjacent cables, and we recorded that results. But we also looked at the deck deformation profile for that unit load. So that's one pair of cables we applied the unit load to, and then we did the same exercise with another set of cables. You capture the results of the cable forces and you capture the deformation results. And you do this with each set of cables. And once you've got some data, which is, I think it would be about, what is it? Yeah, 12 sets of deformations. The way your forward building FEM model works is that it sums up those construction stages, so that at the end of the cable installation stages, your deck profile should look something like this target profile. But because we've used an arbitrary number, 1000 kilonewtons, Obviously, when you sum up your first set of deformations, you would have a poor deck profile. But then what you can do in a simple Excel-based program is you can linearly scale each one of those load cases so that when you sum up all of those construction stages, you get to the desired profile. And so we chose to do this with this manual approach because you have quite a bit of control of the numbers. And obviously the system is highly nonlinear. So this linear approach, you'd have to do a few iterations of these before your forward building computer model actually reaches the desired profile, deck profile. Okay. I know the latest software programs, the Sophistics and Midas and them, they've got this built-in capabilities, but it was good to be able to control the results. Okay, and then on the hanger cables, what was used is this fully locked coils by Radiali, 76 millimeters in diameter with a breaking force of 5,790 kilonewtons. These cables were manufactured in Italy, and we had to finalize the cutting lengths of the cables quite a bit in advance, so that they could arrive on site in time for the contractor, shipped and offloaded. And I think what's a bit tricky with using these fully locked coils with the turnbuckles and is that you have to be quite accurate with your predicted unstretched length. It's maybe not as forgiving as using a parallel strand wire system where you can cut on site. So I think that took quite a bit of energy in determining what the unstretched lengths were. And then on the installation, there's just a few photos of the installation. When the cables eventually arrived on site, the contractor came up with a C-hook to install the cables under the arch, as you can see in the photo over here. So the tower crane lifted this cable with a C-hook, and we also had to be very careful with how we handle the cable so that you don't bend the cable unnecessarily. And they used a template to make sure that that stays within the radius limits. On the tensioning sequence, the designer chose to install and tension what I call the outward leaning cables first. And an interesting aspect, this is now a V configuration stay cables, but what's interesting about these outward leaning cables is that the force applied onto the arch is actually pointing outwards because of the orientation, which means that that sort of force applied onto the arch is pointing outwards and pulls the arch down. So the arch is not really stiff when applying that load. Whereas the inward leaning cable, which is the cable in gray here, has the vector orientation pulls inwards, and this cable is almost perpendicular to the arch curvature, and the arch is very stiff when these cables are tensioned, and your result is that you pick up the deck. It has a better effect of pulling up the deck with the inward leading cables. Okay, and then onto the actual tensioning operation. I'd like to compare this process to a normal pre-stressing operation on a bridge, in that in the sense that when you tension, you're tensioning to the force in the jacks, which are the two red cylinders at the top. But you, at the same time, even though you're tensioning to the force, you still have to control the elongation of the cables. And the way we control the elongation of the cables is by checking these dimensions D2 and D1. It may not be as simple as pre-stressing extension measurements, because the arch rib is quite flexible. So you've got a point on the far side which moves quite a bit. And on the near side, you've got a lot of seating and movement in the fork socket joints. So all of those sort of movements and the extension of the cable has to be taken into account when you're trying to check the elongation of the cable. As I mentioned, you would jack with those jacks. You would jack to the design force, and then you would turn the buckle and lock in the cable. But when you lock in the cable, as on the previous scheme picture, the system has to seat, and when the system seats itself, there is some sort of movement that happens in that area, and that could cause a loss in cable force. And what our team did on site was that after tensioning, they would do another lift-off test to see how much kilonewtons we lost due to the seating, and they would make adjustments on site to rotate the turnbuckle to account for those seating losses. So it is quite a process. And also at the same time, yes, we do tension to the force, but it was also important to monitor the structural deformations, because the arch and specifically the arch is quite flexible. So I know on this graphic we have here in the top right, it shows only 1 millimeter or 2 millimeter deformation, but on some of the stages, the arch moves quite a bit. So our team was continually monitoring the movements of the structure during tensioning. On instrumentation, we only monitored the structure during construction. We don't have a permanent instrumentation system, but we work very closely with the University of Cape Town. And they were able to assist us with a few tests. The first one is the measuring the cable forces with this like ambient vibration testing, which is basically accelerometers attached to the cables, which picks up the natural frequency of the stake cable. So the University of Cape Town's team would come after a stage of cable tensioning, and they would measure the natural frequency of each cable after a stage of tensioning. And as you can see in the screen on the right, it does get a bit tricky with the shorter cables, because the boundary conditions, which is the fork socket, is not it's not a simple pin or a fixed condition. So you would need to model it properly to really get a proper estimate of what the cable force is. So our colleague Kabo, he's busy doing his master's dissertation on, and this is a part of what he's doing is modeling. He's created these sub-models of the cable so that he could, and then he tensions the cable in his analysis program, and in that way he's able to match what the natural frequency on the computer versus what we've measured on site, and then calibrate that to get us an accurate cable tension that's actually in the cable. Similar to measuring the natural frequency of the cable, we've also picked up the natural frequency of the deck with the same accelerometers placed on the structure. And this information, I suppose there's two uses for this information. The first is that you're able to calibrate it with the model that we've created, and to give us confidence in our forward building model. And the second reason why the natural frequency is quite useful is that it gives us a signature of the bridge on completion, almost like, what do they call it, a birth certificate. So we would document the natural frequency of the bridge on completion of construction, and then document in our construction manual, so that if there are issues with the bridge in the future, they would always be able to refer back to the healthy frequency of the bridge. Similarly, we also ran a few tests on completion of the bridge with heavy vehicles. We installed resistance type strain gauges on the soffits of the important structural members, and then we ran the truck through on it, and we picked up the strains, and this information will also, you're also able to calibrate it or correlate it with your software program, but you also capture it in your manual for your bridge, so that the behavior is captured. Okay, that brings me to the end of my section. I'll let Abe close out the session.
Thank you, Heinrich. I trust that we've still got a few minutes left, Mr. Chairman, but we'll be fast on the last few slides.
No problem.
Yeah, so the transverse launch, that was obviously one of the everything built up to this day on August last year. We had live streaming of the event and so on, so that we made sure that everybody could get the benefit of the experience. One of the aspects that had to be looked at carefully was the relative vertical displacement of the new abutments versus temporary abutments. And we did extensive geotechnical testing, continuous surface wave assessment, and also monitoring of the temporary structure as we placed the load on the abutments. And we predicted relative displacements of below, well, the geotechnical guys said below millimeter, but we rather referred to it as less than 5 millimeters. But getting to the east-west abutment, when we started excavation, we ran into some problems with varying founding level, and we found that there was a unexpected dip in the founding layer, the in-on layer that we intended to found, and it also was we actually had severe dewatering issues, and the temporary support or lateral support system was also not deep enough to achieve open excavation to those depths. So over the December period, we managed to get piling contractors onto site, and we converted that abutment to a piled foundation, and also modified the footprint slightly to balance our pile loads, and obviously all the settlement and loading constraints were taken into consideration. On the launch, this was part of the contractor's responsibility, and they involved Naledi engineering to a specialist in this type of exercise to design the system. Our original requirement was that a push system was required because of concerns if you have a single pull system that once the deck starts moving, you won't be able to guide it properly with the extensive elongations that will occur with your tensioning cables. That problem was solved by providing equal jacking forces on both sides, so that your system is or your bridge is launched in a controlled fashion. But this also required extensive retrofitting of the temporary abutments that had already been completed prior to this assessment of the launch, and also the impacts or the influence on the permanent abutments with your highly focused launch forces on each side. The other aspect of this launch was obviously your launch path, and that required very accurate construction methods to make sure that we have a very smooth launch path. Sorry, I jumped a slide there. So the launch bearings were constructed from using two custom-built 900mm diameter pot bearings, obviously to cater for rotation forces, and also to accommodate the pre-stress strand anchorages, which is basically a conventional pre-stress strand anchor that was embedded in the bearings. And then we also had rolling side guides, which eventually came into operation in the final launch quite significantly. These are just some visuals of your launch bearing, which arrived on site pre-assembled. The steel box was filled with high quality concrete, and the bearings were, the sliding pads were special Teflon pads, dimpled Teflon pads. And then there was also, during this whole process, we had to restrain the structure with specially designed pins to be sure that it's stable during all stages. So we had in the design, there was also supplementary force jacks. So we had actually two jacks on each side, the primary jack and then a secondary jack in case our friction or the friction estimations were underestimated, because keeping in mind that the contractor basically had a weekend to do this operation, and we couldn't permit closure of this major route for an extended period. So the final system, there you can see some pictures that we had. In fact, the whole jacking system with the control and so forth was specially imported from VSL. including a very experienced operator, which proved on the day how important it is in a launch like this, because managing all the components, the rate of launch, and so on, there was no time for any teething problems, and we were very satisfied with the way the operation went on that day. It actually went a bit faster than we predicted, which was not usually the case with these once-off launch operations. That's just some closer pictures of the launch bearings, the launch pads being swapped as the bridge gets steered into position, and you can also see the side guides, which we've fed with packers to actually guide the bridge as it moved across to its new position. Just some statistics. The system was originally designed for up to 11%. The primary system was 8%, and then we had with the secondary system, we could cater for up to 11% friction. And in fact, the frictions were below 2% eventually, which is a testimony to the accuracy of the slide path, and also the whole system that was developed and installed by the contractor and his designers. The settlement on the abutments was less than 3 millimeters, and the final launch took 10 hours. Having said that, we did a test launch the weekend before we actually had to stop the contractor about 5 meters because so much was happening on the day of the launch. The public was informed, the client, there was VIP touring groups, and it was actually quite an event in the final analysis. And that, in conclusion, that's just a drone picture of the bridge in its position with the temporary works you saw earlier on exposed. These are the acknowledgements. We were very fortunate to be awarded the Fulton Award for infrastructure and also a commendation. A few shots of some of the team members. We also, in this whole process, there's a lot of parties that were involved, but most notably our client with their vision to enhance the infrastructure, but also provide facilities that not only becomes landmarks for themselves, but also for the community around. We've received very positive feedback, and the exposure that this project has brought to this region has already enhanced the tourism trade, and all these aspects which you don't generally bring into your cost models, provided there's a lot of food for thought. Thank you. I think that's a final picture, and Heinrich is going to switch on a time-lapse video of the launch while, Mr. Chairman, you can start. We're ready for any questions that may have come through on your feeder line.
Well, first, while the time-lapse runs, and before we get to the questions, to both Abe Newmark and Heinrich van Wijk, thank you very much for a very clear presentation, excellent slides and excellent photos, and congratulations to the whole team, to the two of you, but also to the contractor and the client. I think excellent product. Well done. We've got a few interesting questions, some of which may have been addressed in the presentation, but let's see. There's thank you. A question from Tanzania. Katitula, thanks for mentioning where you're from. Asking about the load transferring, that was while you were talking about the horizontal pre-stress load transferring, whether that would be the same as those for cable stayed bridges and extra those bridges. Maybe Heinrich should be the one answering here.
Yes, so I think there are some similarities, but obviously the way you would model it and the type of software you would use, there are definitely similarities. But I think with those types of bridges, the construction method would also play a big modeling perspective. There's a lot of similarity to do stake.
It sounds as though okay, Heinrich, it would seem that you disappeared for a moment there. Maybe the last 2-3 sentences. Can you come back again with that?
Yes. So I was saying from a modeling perspective, there is quite a bit of similarities, and if you did the one structure, you would probably have an idea how to apply it onto a cable stay structure or extra dose. But I'm sure in terms of constructability and in terms of how the structure works, obviously there would be differences.
Okay, thank you. We've got a few questions from the same participant. I'll take another one from him and then I'll jump to another one. But the next question was controlling of the elongation of the tension structure, comparison with estimates. How did you do that and what did it come out to? But I think you addressed that, but maybe quick overview.
I think we're referring here to the hanger strands, and I think the computer model, a big part of the measurements that you take on site is structural deformation and elongation of cables, and I think our computer models were quite accurate with calculating the deformation of the arch. Of course, it's not as so, which means that our cable elongations, they were relatively accurate, but they wouldn't be as accurate as the elongation comparison for pre-stressing system.
Okay, thank you. And then I'm going to jump to another anonymous attendee. How did you calibrate the model in Sophistic? It would be nice to hear an answer on that.
I think the nicest way that we could get a real calibration, this is a cable supported structure, so the cable forces are very much dependent on the self weight of the structure. So that's something you have to make sure you get correct. And we had a phase when we were installing the permanent bearings after close towards the end of the structure, where we were able to jack up the structure and install the permanent bearings. So when we did that operation, when you jack up the structure, you're able to get to the real weight of the structure. And we used this mass information to update our model so that the self weight was accurate. And I think when your self weight is accurate, your cable force is also it's directly your self weight of your structure is directly related with your cable forces. So that was one of the ways that we calibrated the model.
Yeah, and
Okay,
thanks. Maybe I can just add, there was quite due to the construction process, there was quite a delay between the stage 2 and stage 4 tensioning, because we did or the stage 3, we did with the bridge in its original position, and stage 4 we did with the bridge in its final position. So that allowed us to monitor displacements and also look very carefully at our time-dependent behavior over that period, and bearing in mind that a lot of your creep and shrinkage happens in the first 6 to 12 months. So that gave us the opportunity to back check with those values, which in a structure like this becomes quite significant values, and you can't really just rely on codified values. We actually did lab tests on that as well, which we also brought into the equation.
Thank you. Interesting. Abe, maybe for you, there's a question about construction cost per square meter. Now, we've got an international audience, so maybe you should express that in maybe dollar per square meters. Maybe compare that with what another structure would have cost, if all of that is possible.
Yeah, we did some comparisons the other day, and I think we were on a similar project in the Western Cape. We currently up at about 40,000 Rand a square meter for 35 to 40,000, depending on founding conditions and so forth. And this one, we actually went up to about 50 to 60,000 Rand a square meter. So we're looking at a premium in this instance for the capital costs of about 35% more. But once you bring in your road user costs, this being a premier route, it eventually pointed to about a 10% additional cost. That's just using straightforward road user cost benefit figures. What also happened in this instance is as some of you may know, our contractor went into business rescue and delayed the project by about 2 years, which is something one doesn't usually take into consideration. But in this instance, it actually, I think if we had this route under stop-go control for 7 years, it would have been quite detrimental to the local economy, because the route crossing this bridge to the eastern part of South Africa, there's 2 major arterials, and you could imagine what the implications were on that. So I think one can't always bring that into the equation, but one also has to look at the bigger picture. Another aspect that one has to, the total project cost was about 6 times more than what, or 7 times. Yeah, the bridge was a relatively small percentage to what the total project cost. So that's also a way to look at it, and not just. I'm not saying one should ignore all the bridge economy in your assessment of the structure type, but one should look at everything holistically. Even the economic value we've now added to the region for tourism and so forth.
Okay, thank you. Just for the international audience, the numbers that Abe was mentioning brought us to somewhere about $3,700 a square meter, if that is, if I make the correct calculation. And another question, Heinrich, from the Tanzanian who's attending. I'll take 2 of his questions in one. One was the minimum strength of concrete to allow tensioning. And then the other one, is there any allowance for inspection and maintenance during the life of the structure, like platforms or access for people to do maintenance?
Okay, so for the first question, when you say tensioning, for the post-tensioning, we normally have about, I'd have to check the numbers, but it's about 30 odd MPa for post-tensioning.
We also, just to come in there, we also have a minimum time limit of about 21 days.
Yes,
Because to limit early creep.
that's right. There wasn't a criteria for the hanger tensioning because the concrete would have reached full strength, which the major structural components was 50 MPa concrete for the tie beams and the arches. So they would have reached full strength on hanger tensioning, and that's cube strength. And the second question was related to maintenance. So there is quite a comprehensive maintenance manual that's put together for this structure. And I think there are eye holes. You just have to correct me if I'm wrong here, but there is temporary
Eye bolts
connected on the top of the arch ribs, so that the type of abseiling team can gain access if necessary on the top.
Yeah, we actually found that because the height of the structure allows very good access with normal cherry pickers. And this is probably a first for our client. We've developed, because it's a fairly significant structure, we've compiled in consultation with our UK team, who's got extensive experience with complex bridges. We've compiled a maintenance manual for the structure service life, and that manual, so that all the tensioning operations and predictions and forecasts and everything, and the critical components, how they should be inspected, and in the event of hanger out scenario due to a vehicle collision, what procedures need to be undertaken, and how the structure can be reinstated to its serviceable condition, and so on and so on. So I think that's something that that is actually quite important, not to lose all the knowledge and input for the future generations, because the estimated service life of a structure like this is probably over 100 years.
Thank you, Abe. Then another question of my own, maybe a bit more general, but you elaborated a little bit about the aesthetics of the bridge. Was there a bridge architect involved, or was that all done from the engineering side?
Basically, no, everything was done from the engineering side. There was one or two examples that we came across. I think there was a bridge very similar to this one done in the States. So that provided us with a lot of guidance. But I think the fine-tuning, the cable layouts, and the shaping at the arch, the balustrade. You will notice the balustrades also simulate the arch sort of shape. All that was done from the engineering side. We're not against using architects, but in this instance, it wasn't done.
Okay. You also mentioned right in the beginning the image that you showed from Revit. Did that Revit model go any further, and is that one way to capture some of the as-built information?
Yeah, we haven't got to the stage where currently all our bridges are detailed using Revit, so that's probably something that will happen in the future. But in this instance, we just modeled the concrete sort of outlines and so forth in Revit. But we found that very useful in terms of visualizing the structure and obviously for giving the client some feel. We actually did a VR simulation with the client with that model, which was very effective. So the client was provided with those VR visual units, and they managed to walk all over the arch and stand on the top and so forth. So yeah, but, in a practical sense, the Revit 3D modeling is now becoming quite a reality on all our projects, and you're quite right that all that data needs to be preserved for future use rather than just the hard copy or the PDF copies, whatever you call it. The young guys know all the terms. But what we also realize is that the contractor and his laborers, they still primarily use 2D drawings to construct. So one needs to, with all this 3D visualization, you still need to keep in touch with that part. Otherwise, the guy that actually has to build it is going to struggle a lot. So we tend to combine 3D visualization to expand the 2D models.
Okay, thank you very much. I don't see any other questions coming up, and I think maybe it's Friday afternoon, at least where we are. So I would like to really thank Abe Newmark and Heinrich from Wijk for their contribution. Congratulations once again to the two of you, but also to your teams. Impressive engineering that you've explained to us, and we really appreciate it, just being exposed to that. Thank you. I see there's a question about PowerPoint slides, whether that's made available afterwards. I think I'm not so sure what the IABSE policy is, but we'll discuss that with the office and maybe with the presenters, and then we'll come back to the participants. Before we sign off, I want to thank Brenda and Firat in Zurich, who managed to set this up for us, all the technology and the advertisement and marketing for the presentation. Thank you to you. And then thank you to all participants for the time that you spent with us. I think that was a very valuable participation that we had. So thank you once again, Heinrich and Abe. Enjoy your weekend. Thank you.
Thank you very much from our side, and thanks for the extra time. We overshot to the audience as well. We overshot our whatever, but when you're passionate about something, it's difficult to contain yourself.
Thank you.
Thanks.
Well done. Thank you. All right. With that, then I think Brenda, you can probably close the session for us.